Today we are going to be working on something called partial fractions. And partial fractions are something that you've been doing for a long time in algebra in reverse, but you've never done it forward. For instance, if I gave you these two fractions, and I told you to combine them into a single fraction, you would know exactly what to do. You would multiply the first fraction by x minus 2 over x minus 2, and you would multiply the second fraction by x plus 1 over x plus 1. And the whole purpose of that is that now they have a common denominator, and so you would have x minus 2 plus 3x plus 3 over the combined x squared minus x minus 2. And if we were to reduce the top combined like terms, we would have 4x plus 1 over x squared minus x minus 2. There you go. We have combined the fractions. But what if I asked you to integrate 4x plus 1 over x squared minus x minus 2 dx? Well, we could try a u sub, and our standard u sub would be whatever's on the bottom. The problem is, for this one, that du is 2x minus 1 dx. So we can see that the coefficient of x and the constant are a factor of 2 different. But unfortunately, what we actually have in the numerator is not a factor of 2 different between the coefficient of x and the constant. So the question is, well, how do we do this? How do we integrate this expression? But clearly we started from this being the integral of x plus 1 plus 3 over x minus 2. Double check that. Yes. Okay. Now I may not know how to integrate that thing together, but I definitely know how to integrate this. So I can integrate each of those two things separately. Okay? And you would technically do them with the u sub. U equals x plus 1 for the first one, u equals x minus 2 for the other one. But I know that that's going to be log of the absolute value of x plus 1 plus 3 times the log of the absolute value of x minus 2 plus c. If we really felt like combining them, it might be something like this. Keep the absolute values there. X plus 1 times x minus 2 cubed plus c. Piece of cake, easy to integrate once we've broken down that fraction into 2 separate fractions. But this is something that you've never done before. You've never taken 4x plus 1 over x squared minus x minus 2 and changed that into 2 fractions. You've always done it the other way around. And so all the method of partial fractions is figuring out how to separate a fraction into 2 other fractions. Okay? So the procedure is actually very easy. Okay? We are going to assume that our answer is going to look like ax plus b. Oh wait, check that. First, we're going to break it down into a factored denominator. And we have x minus 2 and x plus 1, just like before. Okay. Now we're going to assume that our answer is a over x minus 2 plus b over x plus 1. Okay, those are the two fractions that we're going to try to break it into. And then we're just going to work our normal magic. Let's combine it into one fraction. We've got a times x plus 1, and we'll have b times x minus 2 all over our combined fraction, or our combined denominator, x squared minus x minus 2. I'm going to multiply everything out and combine like terms again. So we've got an ax plus a plus bx minus 2b over x squared minus x minus 2. So how much x do I have? I have a plus b. And how much constant term do I have? I have a minus 2b. And this was equal to, if you remember, our original 4x plus 1 over x squared minus x minus 2. Well, the denominators are the same on both sides of the equation. So clearly, 4x plus 1 equals x times a plus b and a minus 2b. Now here's something else that you've never done before, which is it looks like we've got a lot of variables floating around and only one equation. Two unknowns, a and b, but one equation. But think about it this way. If x increases by 1 on the left, x is going to have to increase by 1 on the right as well. So actually, this 4 has to be the same as a plus b. And think about if x were 0, for instance. If x were 0, then clearly the 1 would have to be the same as a minus 2b. So I can actually set up two equations from this one equation. All the stuff that has to do with x. On the left, that's 4. On the right, that's a plus b. And all the stuff that is just a unit. On the left, that's a 1. And on the right, that's a minus 2b. Now I have two equations of two unknowns. No problemo. So I'm going to choose to subtract because that'll get rid of my a's. So 4 minus 1 is 3, a minus a is 0, b minus negative 2b is 3b. So b is 1. And now I can plug that into either of the equations. I'm going to use the top one because 4 equals a plus 1. So a plus b, 3. Go this way. 3 equals a. Remember we said that was a over x minus 2 plus b over x plus 1. So apparently it's 3 over x minus 2 plus 1 over x plus 1, which is how we started the whole session. Okay? So that's it for partial fractions. Let's review. We're going to do one more. Step number 1 is factor the denominator, and if we need to, expand the numerator. Okay? That way we'll have a bunch of stuff multiplied by x squared, a bunch of stuff multiplied by x, and a bunch of constant stuff in the top. In the bottom, it's all factored. 2, set up the different fractions based on the factor denominator. Okay, that's step 2. Step 3, combine all fractions. Okay, we do that with common denominators. Step 4, set up, I don't want to say this, set up equations based on powers of the numerator. And then you're done. Well, I guess we could have a step 5 here. Solve equations. And of course, the whole reason we're doing this is to break it up into multiple fractions so that we can integrate. Okay, so those are the 6 steps. Factor the denominator and expand the numerator, and then the rest. Okay, let's look at a slightly more complicated one, but not that much more complicated. Let's look at x cubed plus 3x. That's not what we want to do. Let's look at 2x minus 1 x squared plus 1 squared. Now, I could have multiplied this denominator out, in which case the first step again would be to factor it. Okay, so we sort of skipped having to factor it. Now, we've got a few terms here to deal with. We'll go over these more in class. This x just gets to be an x. Okay? Notice that we have a factor of x squared plus 1. So we need a factor of x squared plus 1. But we also have a factor of x squared plus 1 squared. Okay? The two are sort of combined. But we need them both in there. Okay? And the reason we need them both in there is, for instance, if we have 3/4, we could break that up into 1/2 plus 1/4. Okay, so when something is squared, not only do we need the original factor, but we also need the original factor squared in order to catch all the possible terms. Okay, so because we have that squared term, not only do we need an x squared plus 1, but we need an x squared plus 1 squared. So we need both of those. So that's one difference here. The other difference comes from something that I didn't tell you the first time we went through this, which is that the numerator has to be 1 degree less than the denominator. So when it's just over x, you can leave that as a. Okay, just like before, this x plus 1, we just had a constant over it. X minus 2, we just had a constant over it. However, look at this one, it's x squared plus 1. So we need a polynomial that is 1 degree less. So we're going to say that that's bx plus c. The nice thing is that this x squared plus 1 squared Ignore the second squared. This is still, the factor on the bottom is x squared plus 1. There happen to be two of those factors, but the factor on the bottom is x squared plus 1. So I'm going to call this dx plus e. Just has to be linear. Okay, now we have to combine the like terms. So a has to be multiplied by x squared plus 1 squared. The bx plus c has to be multiplied by x squared plus 1. And the dx plus e just has to be multiplied by x. And all of that is over our x squared plus 1. And that's equal to x minus 1. X times x squared plus 1. Our denominators are the same, so we can start ignoring them. 2x minus 1. And now we get to multiply everything out. This is x squared plus 2x plus 1. So we have ax squared plus 2ax plus a. How much bx am I going to have? Well, this part here, we write as x cubed plus x. So bx times x cubed is bx to the 4th. Then we have a bx times x, so that's bx squared. Then we're going to have a cx cubed and a cx. And last but not least, we're going to have a dx squared plus dx. Okay? So this is what we have. Now, our highest power that we're dealing with here, apparently, is 4th power. That thing's got a 4th power. So let's take a look. X to the 4th. How much x to the 4th do we have on the left side? The answer is none. We don't have any. How much x to the 4th do we have on the right side? It's bx to the 4th. Hey, we already solved for one of our 5 variables. Awesome. X cubed, we've got 0 on the left-hand side. And we have c on the right-hand side. So it looks like both b and c happen to be 0 for this one. That's nice. X squared, we have 0 on the left. We have a plus b plus d on the right. X, we've got 2 on the left. And we have 2a plus c plus e on the right. And our constant term, which you could call x to the 0 if you wanted to. We have negative 1 on the left. And we have a, and that's it. On all of these problems, this is sort of how it's going to turn out. It may look like you've got 5 variables, but you really, these multiple equations, multiple unknowns, sets of equations that you have, will be really easy to solve. So a equals -1, b equals 0, c equals 0. Now I just need to solve for b and e, and we'll be done. So that's 0, that's -1, so d must be 1. This is -2, c was 0, so e must be 4. So our original fraction, which was 2x minus 1, x times x squared plus 1 squared, is -1 over x plus 0 of that other fraction, and then x plus 4 over x squared plus 1 squared. So if we were going to integrate, now we would just integrate this one, which is going to be negative log of the absolute value of x. And then we'd have to figure out how to do this one. Let's do that. X. There's a dx. First part's easy. Negative log of the value of x. To do the second part, we can break it up a little further. We've got x over x squared plus 1 squared dx. And we have 4 over x squared plus 1 squared dx. We can see what we can do with either of those. Okay, this one is just going to be a u sub. And I hope by now you know that this one is going to be a trace sub. Okay? I'm not going to do those now because the purpose is to make sure that we understand how to do the partial fractions. Okay, so that's pretty much the end of it. I'm just going to add to this list here where it says set up fraction, number 2. Set up fractions based on the fraction denominator. Here's a 2 star. Okay. If it looks like 5x plus 3 on the bottom times x squared times x squared plus 1. Okay. We're going to break it down into each individual term, 5x plus 3, plus this monomial here could be 1 over x. We also have a 1 over x squared. And for our x squared plus 1, now we're dealing with a quadratic. And so we would have, they're not 1s though. Add the number. A, B, C. And this one would be dx plus e. Okay. Little tricky here. But notice that's different than x squared plus 1. This is an x times an x. So we need the x term and we need the x squared term. And that's all there is to it. Okay? So the key is breaking it down into any fractions like this, and we'll be able to integrate any of these fractions because they're either linear on the bottom, like this one or this one, in which case it's just a u sub, and it'll end up being a logarithm. Okay? If it's x squared on the bottom, okay, we know how to integrate x to the negative 2. X squared plus 1, arctan. Integral of 1 over x squared plus 1 is arctan. So we're always going to be breaking stuff down, breaking the fractions down into things that we already now know how to integrate. And so that's the way the partial fractions work, and that's why we have to know how to use them.